Welcome to this walkthrough of LeetCode problem number 257, binary tree paths. In this session, we'll explore how to traverse a binary tree and extract all possible root-to-leaf paths. By the end, you'll have a clear understanding of the approaches and the concepts involved.
Let's get started. In this problem, we're tasked with finding all root-to-leaf paths in a binary tree.
A root-to-leaf path starts at the root node and ends at a leaf node, where a leaf node is defined as a node with no children.
The paths can be returned in any order. Let's discuss the input and output format.
The input is the root of a binary tree, represented as a tree node object. Each tree node has three properties: a value, a left child, and a right child, where the child nodes can be null if they don't exist. The output is a list of strings, where each string represents one root-to-leaf path. The path is formatted with nodes connected using arrows, like node 1-node 2-leaf. This format makes it easy to understand the entire sequence of nodes from the root to each leaf.
To clarify the problem further, let's look at an example.
Suppose the input is a binary tree represented as root equals 1, 2, 3, null 5. The tree structure looks like this. The root node is 1, which has two children, 2 on the left and 3 on the right. Node 2 has a right child, which is 5, and no left child.
Node 3 is a leaf with no children.
The output for this tree would be 1-2-5, 1-3. These strings represent the two paths from the root to the leaves. One path goes from 1 to 2 to 5, and the other goes directly from 1 to 3.
This example demonstrates how we can traverse the tree and represent each path as a string.
Breaking down the output further, the binary tree in this example has two distinct paths. The first path starts at the root, 1, goes through the left child, 2, and reaches the leaf node, 5. This path is represented as 1-2-5. The second path starts at the root, 1, and goes directly to the right child, 3, which is a leaf.
This path is represented as 1-3.
Together, these paths make up the output list. Now, consider a simpler case where the tree contains only one node. For instance, if the input is root equals 1, the tree consists of just the root node, which is also a leaf. In this case, there is only one path, 1, and the output is a list containing this single string, 1.
In the case where the tree consists of only the root node, the explanation is straightforward. Since the root node is also a leaf, the only path in the tree is from the root to itself. This path is represented as 1, so the output is 1. Now, if the input is an empty tree, represented as root equals, there are no nodes in the tree. This means there are no root-to-leaf paths to return. The output, in this case, is simply an empty list. These examples highlight how the tree's structure directly affects the output. When the tree is empty, there are no nodes and, therefore, no root-to-leaf paths. The output is an empty list in this scenario.
Now, let's discuss some constraints and edge cases. The number of nodes in the tree can range from 1 to 100, and node values can be between -100 and 100. Several edge cases are worth noting: a tree with only one node, an empty tree, a highly unbalanced tree where all nodes are in a single line, and trees that include both negative and positive values. These considerations ensure your solution is robust and handles all possible inputs correctly. To solve the problem of finding all root-to-leaf paths in a binary tree, we explored several approaches. The first one is the brute force method, which uses an iterative depth-first search, or DFS, approach with a stack. The intuition here is to explicitly simulate the recursive DFS process by maintaining a stack that stores tuples containing the current node and the path string leading to it. As we traverse, we keep appending child nodes to the stack, and whenever we reach a leaf node, that is, a node with no left or right children, we add the completed path string to our result list. This approach has a time complexity of O(n), as every node is visited once, and a space complexity of O(n), in the worst-case scenario of a skew tree. While this method is straightforward and avoids recursion, managing the stack and path strings manually can become verbose and error-prone, which is a notable drawback.
Another approach is to use recursive DFS with backtracking.
This method builds the path string as we traverse the tree recursively. The key idea is that each recursive call handles the traversal of one node, appending its value to the path string.
When we reach a leaf node, the current path is added to the result list. Backtracking ensures that as we return up the recursion stack, the path string is correctly updated, avoiding any state management issues. This approach also visits each node once, so the time complexity remains O, n, and the space complexity is O, h, where h is the height of the tree, due to the recursive call stack. The method is clean and intuitive, as it aligns with the natural structure of the tree, but one downside is that it can run into stack overflow errors if the tree is extremely deep. A third option is breadth first search, or BFS, which uses a queue to traverse the tree level by level. For each node, we keep track of the path string accumulated so far. When we reach a leaf node, we add the path to the result list. While BFS handles wide trees better than DFS, it often requires more memory than DFS for deep trees, making it less efficient in those cases. Among these options, we chose the recursive DFS approach with backtracking as our preferred strategy. This decision was based on a few key observations. First, recursion naturally mirrors the hierarchical structure of a tree, which makes the implementation simpler and more intuitive. By building the path string during traversal and using backtracking to revert changes when moving back up the tree, we maintain accuracy without additional memory management overhead. Although iterative DFS and BFS are valid alternatives, their respective drawbacks, such as verbose stack handling and higher memory usage, make the recursive approach a better fit for this specific problem. One pivotal realization here was that backtracking not only simplifies state management but also ensures correctness by preventing redundant computations, keeping the solution both efficient and elegant. When we compare the trade-offs, the recursive DFS approach stands out for its balance between simplicity, clarity, and performance. Unlike iterative DFS, it eliminates the need for explicit stack management, which reduces code complexity. While BFS can be useful for certain scenarios, such as handling very wide trees, it typically requires more memory and is less intuitive when it comes to generating paths from root to leaf. One potential concern with recursive DFS is the risk of stack overflow in the case of highly skewed trees, but this can often be mitigated in practice with balanced trees or by switching to an iterative approach if necessary. Ultimately, we selected recursive DFS because it aligns naturally with the problem's requirements, avoids unnecessary complexity, and performs well for the majority of typical inputs, making it the most practical and efficient choice overall. The problem we're tackling here is LeetCode number 257, binary tree paths. The task is to find all root-to-leaf paths in a binary tree, where each path is represented as a string of node values joined by dash. A root-to-leaf path starts at the root node and ends at a leaf, which is a node without any children. To solve this, we'll use an iterative depth-first search approach with a stack. First, we initialize the process. If the root is null, there are no paths, so we simply return an empty list. Otherwise, we set up a stack to simulate the DFS traversal. Each item in the stack is a tuple, the current node we're visiting and the path string leading to that node. We start by pushing the root node along with its value as the initial path onto the stack. This lays the groundwork for our traversal. Now, we move on to the DFS iteration using the stack. While the stack is not empty, we repeatedly pop the top element, which gives us the current node and the path string leading to it. If the current node is a leaf, meaning it has no left or right children, we add the path string to our result list since we've completed a root-to-leaf path. On the other hand, if the current node has children, we process them. When there's a right child, we push it onto the stack and update the path string by appending the right child's value. Similarly, if there's a left child, we push it onto the stack with the updated path string. Once the stack is empty, all paths will have been explored, and we simply return the result list containing all the root-to-leaf paths. At this point, let's highlight some key insights about the algorithm. Using a stack allows us to simulate the recursive DFS process iteratively, which is useful for avoiding stack overflow issues in case of deep recursion. By storing the path as we go, we eliminate the need to reconstruct paths during backtracking, making the approach more efficient. The order in which children are pushed onto the stack also matters. By pushing the right child first, we ensure the left subtree is processed first, maintaining the traversal order of recursive DFS. Additionally, we determine whether a node is a leaf by checking if both its left and right children are null. This condition forms the basis for terminating a path. The main data structures we use include the stack, which keeps track of nodes and their associated paths, and the result list, which collects all the completed paths.
In terms of complexity, the time complexity is O, n, because we visit each node once. The space complexity is also O, n, in the worst case, accounting for the stack and the result list. To solidify our understanding, let's walk through an example with a binary tree. The root node is 1, which has two children, 2 and 3. Node 2 has a right child, 5. We start by initializing the stack with the root node and its value. Stack equals 1, 1, and the result list is empty. First, we pop the root node 1 from the stack and push its children 3 and 2, updating their paths to 1-3 and 1-2. Next, we pop node 2, pushing its child 5 with the path 1-2-5. When we pop node 5, we find it's a leaf, so we add 1-2-5 to the result. Then, we pop node 3, which is also a leaf, and add 1-3 to the result. With the stack empty, we return the result list 1-2-5, 1-3. This example demonstrates the algorithm in action, clearly showing how we traverse the tree and build the result step by step. This Python solution implements the iterative depth-first search (DFS) approach to solve LeetCode problem number 257, binary tree paths. Let's go through the code step by step. First, the tree node class is defined to represent each node in the binary tree. Each node has a value, val, and pointers to its left and right children. In the solution class, the binary tree paths method is implemented. It begins by checking if the root node is none. If the tree is empty, an empty list is returned since there are no paths to compute. We initialize an empty list paths to store all root to leaf paths and a stack initialized with a tuple of the root node and its value as a string. The stack enables us to traverse the tree iteratively. The core logic lies in the while loop, which runs as long as there are nodes in the stack. Each iteration pops a node and its associated path string. If the node is a leaf, both left and right children are none, the current path string is added to paths. For non-leaf nodes, the right child is added to the stack first, if present, followed by the left child, if present. This ensures that the left subtree is processed before the right subtree, maintaining the DFS order. Finally, once all nodes have been processed, the paths list containing all root-to-leaf paths is returned. This solution efficiently handles edge cases such as an empty tree or a tree with only one node. By using an iterative approach, it avoids recursion-related stack overflow issues in deep trees. The overall time complexity is O, n, where n is the number of nodes, as each node is visited once, and the space complexity is O, h, where h is the height of the tree, due to the stack storage. Here, we start by importing the necessary utilities and defining the structure of a binary tree node. Each node has an integer value, val, and references to its left and right child nodes. The tree node class includes two constructors, one for creating a node with a value and no children, and another for creating a node with a value and specified left and right children. Next, we define the solution class, which contains our main method binary tree paths. This method takes the root of the binary tree as input and returns a list of strings representing all root-to-leaf paths. We first handle the edge case where the root is null by returning an empty list, ensuring that our solution gracefully handles an empty input tree. We then initialize an empty list, paths, to store the final root-to-leaf paths. To facilitate iterative traversal, we use a stack, where each element is a pair consisting of a tree node and the current path string leading to that node. We push the root node along with its value as the starting path. As long as the stack is not empty, we pop the top element to process it. If the current node is a leaf, meaning both its left and right children are null, we add the current path to the paths list. Otherwise, we check for the existence of the right and left children. If they exist, we push them onto the stack along with the updated path string, appending the child node's value to the current path. This ensures that paths are built incrementally as we traverse the tree. To manage these node path pairs, we use a pair class, which stores two related objects, a key and a value. Here, the key represents the tree node, and the value represents the corresponding path string. The pair class includes a constructor to initialize the key and value, as well as getter methods to retrieve each. While the code uses JavaFX's pair class, you can replace it with a custom implementation if needed. This helper class simplifies managing the relationship between nodes and their paths, keeping the code clean and organized. With this approach, the entire tree is traversed iteratively,
and all root-to-leaf paths are collected in the paths list, which is returned as the final result.
Here, we are working with a simple binary tree where the root node has two children, and one of those children has a right child. To begin, we initialize an empty list called paths to store the final paths and a stack that starts with the root node and its value as the initial path string. In the first iteration, we pop the root node, which has the value 1, along with its path string 1. Since this node has both left and right children, we push them onto the stack, appending their values to the path string. Now, the stack contains the nodes 3 and 2, with their respective paths 1-3 and 1-2. This sets us up to explore the left and right subtrees of the root node. Next, we continue by popping node 2 with the path 1-2 from the stack. Node 2 does not have a left child, but it does have a right child. Therefore, we push node 5 onto the stack along with the updated path 1-2-5. Now, the stack contains node 3 with the path 1-3 and node 5 with the path 1-2-5. Following this, we pop node 5, which is a leaf node since it has no children. As a result, we add its path 1-2-5 to the paths list. At this stage, the paths list contains one entry, 1-2-5. Finally, we pop node 3 with the path 1-3 from the stack. Since node 3 is also a leaf node, we add its path to the paths list as well. Now, the paths list includes both 1-2-5 and 1-3, and the stack is empty, signaling the end of the traversal. At this point, the stack is empty, which means we have finished traversing all possible paths in the binary tree. The paths list now contains the two paths, 1-2-5 and 1-3. We simply return this list as the final output, which represents all root-to-leaf paths in the given binary tree. Moving on, let's explore another example with a simpler tree structure. Now, we look at a single node tree, where the tree consists of only the root node with the value 1. We initialize the paths list as empty and start the stack with the root node and its value as the path string. In the single iteration, we pop node 1 with the path 1 from the stack. Since this node is a leaf node, we add its path 1 to the paths list. At this point, the paths list contains one entry, 1, and the stack is empty. This indicates that we've processed all the nodes in the tree. In this example, the tree has only left children, forming a linear structure. We start by initializing the paths list as empty and add the root node to the stack along with its value as the initial path string. The first iteration involves popping node 1 with the path 1. Since this node has a left child, we push node 2 onto the stack with the updated path 1-2. In the next iteration, we pop node 2 with the path 1-2. Node 2 also has a left child, so we push node 3 onto the stack with the path 1-2-3. Finally, we pop node 3, which is a leaf node, and add its path 1-2-3 to the paths list. With this, the paths list contains the single path 1-2-3, and the stack is now empty. With the stack empty, we know that all paths have been explored. The paths list contains just one entry, 1-2-3, which represents the sole root-to-leaf path in this tree. We return this list as the output, concluding our traversal for this example. This approach demonstrates how the algorithm handles trees with only left children, efficiently building the paths step by step. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. This is because the algorithm employs a depth-first search, or DFS, which ensures that every single node in the tree is visited exactly once. This traversal alone guarantees an O(n) contribution to the time complexity. Now, during this traversal, we construct strings that represent the paths from the root to each node. While string concatenation for a single path of length k takes k time, in the worst-case scenario, such as in a skewed tree, the path length could be proportional to n. However, the total cost of all these concatenations combined still sums to O(n), as each edge or path segment contributes only once across the entire traversal. Putting it all together, the overall time complexity remains O(n). The space complexity of the solution is O(h), where h is the height of the binary tree. This comes from two main sources. First, there is the stack space utilized during the DFS traversal. At any point, the stack holds nodes from the root to the deepest node currently being explored, and in the worst case, such as in a completely skewed tree, this stack will contain h nodes, where h is equal to O(n).
On the other hand, in an optimally balanced tree, the height h is O log n. Second, we store all root-to-leaf paths in a list called paths. If there are L leaf nodes, and each path contributes O, h, space for its string representation, the total space for storing paths becomes O, L asterisk h. In the worst case, where the number of leaf nodes L is proportional to n, this still simplifies to O, n. Therefore, the overall space complexity is dominated by the stack usage, and we can conclude it is O, h. In a perfectly balanced binary tree, the height h is O log n, which means the space complexity becomes O log n. However, the time complexity remains O, n, because every node is still visited once. For a moderately balanced tree, the height h lies somewhere between O log n and O, n, so the space complexity adjusts accordingly, but again, the time complexity still remains O, n. In the worst case, such as in a skewed binary tree, the height h is O, n, which leads to both time and space complexities being O, n. Comparing this to a brute force approach, which might involve visiting nodes multiple times or recomputing shared subpaths, such inefficiencies would result in much higher time complexity, potentially O, n squared, or worse. By using DFS and constructing paths incrementally, this solution avoids such duplication, ensuring optimal O, n, time complexity. To prove the big O bounds, consider the following. First, the traversal cost, each node is processed exactly once, which contributes O, 1, per node, adding up to O, n, overall. Second, for string concatenation, we know that each edge or path segment is used exactly once during the traversal, and since a binary tree contains n1 edges, the total concatenation cost is proportional to O, n. Finally, the stack usage, the maximum number of nodes in the stack at any given time is determined by the height of the tree, h, leading to O, h, space complexity. Combining these observations, we can confidently conclude that the solution achieves optimal performance with O, n, time complexity and O, h, space complexity. When approaching this problem, there are a few common mistakes that can trip up beginners. First, failing to recognize leaf nodes is a frequent issue. Remember, a leaf node is one that has no children, both left and right child pointers need to be null. If you don't correctly identify these nodes, you might either stop the recursion too early or continue indefinitely, which leads to incorrect path generation. Another common mistake involves string construction. If you're concatenating strings as you build paths, you need to ensure the correct separator, like dash, is used. Neglecting this can result in paths that are improperly formatted, which could cause your output to fail test cases. Next, there's the issue of forgetting to reset shared state during recursive backtracking. If you use a mutable list to store paths and don't revert it after exploring a branch, your result might contain incorrect paths. To fix this, you can either create a new copy of the path at each recursive step or manually undo any changes when you backtrack. Lastly, with iterative depth-first search, some fall into the trap of duplicating large amounts of data unnecessarily, like entire path lists, when managing the stack. This is inefficient and can significantly increase memory usage, especially with deep trees. A more efficient approach would be to append nodes to the path dynamically as you traverse. Edge cases are another critical aspect to consider. For example, what happens if your tree is empty? If the root is null, your function should return an empty list instead of throwing an error. Similarly, a tree with just one node is a valid input, and your function should handle it gracefully by returning a single path. Beyond edge cases, this problem is a fantastic opportunity to showcase skills in recursive and iterative depth-first search, as well as string manipulation. It tests your ability to traverse a tree while dynamically building a result. Optimization is key here. Clean backtracking not only avoids redundant computation but also makes your code more elegant. During interviews, you might be asked why you chose recursion over iteration, or vice versa, so be ready to explain the trade-offs. For example, recursion is often simpler and more intuitive, but it can run into stack overflow issues for deep trees. Finally, interviewers may test your solution with edge cases like unbalanced trees or very large inputs, such as a tree with up to 10,000 nodes. Related problems like pathsum2, and some root-to-leaf numbers share similar concepts, so practicing these can help you strengthen your understanding of tree traversal and path generation strategies. There are several alternative approaches you can explore for this problem, each with its pros and cons. Recursive depth-first search is one of the most intuitive methods. It's concise and easy to implement, making it a great choice for smaller trees. However, for very deep trees, recursion can lead to stack overflow, especially in languages that don't optimize tail recursion. Another option is iterative DFS using a stack. This avoids recursion limits and is often preferred in interviews where recursion might be discouraged. The downside is that it requires more boilerplate code and can be error-prone when managing the stack state. Breadth-first search, or BFS, is another approach. While it's more commonly associated with level-order traversal, it can be adapted to solve this problem. That said, BFS isn't as natural for path generation because you need to keep track of parent-child relationships, which adds complexity. For string manipulation, using tools like String Builder in Java or Python's string join method can be more efficient than repeatedly concatenating strings. These techniques minimize the overhead of string operations, but they do add some complexity to your implementation. Each of these approaches has its place, so understanding their trade-offs can help you decide which one is best suited for a given scenario. We've reached the end of our walkthrough for LeetCode problem number 257, binary tree paths. Today, we reviewed the DFS approach and discussed its time and space complexities. Remember, mastering recursion and tree traversal can significantly improve your problem-solving skills. Thank you for watching, and don't forget to subscribe for more coding lessons. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!